This video is an introduction to sequences. A sequence is a list of numbers, either finite or infinite, that is arranged in an order and obeys a certain rule. So here are just two examples of sequences. The first one is 1, 3, 5, 7, 9. As you can tell, the rule that's being obeyed is that a 2 is being added each time, right? A 2 is being added to the term that came before to get the next term of the sequence. In the second example, each term is not related to the term that came before it in that way. It's a different type of sequence. In this one, each term, like term 1, term 2, term 3, term 4, is the term number raised to the power of 3. And I've gotten good at recognizing this kind of sequence, so that's how I was able to pick out the rule like that. You'll get better at picking out the rule as you look at a sequence throughout this chapter. But I just wanted to illustrate two different types of sequences that we might see. So you'll see that the second example is 1 to the third power, 2 to the third power, 3 to the third power, 4 to the third power, rather than something being added each time or subtracted each time. Just to get these definitions down, a finite sequence is one that ends. So sometimes we're only interested in a certain number of terms, like this example, 6, 12, 18, 24, 30, and then it stops. And an infinite sequence, just like it sounds, is one that never ends, and we show that by putting a dot, dot, dot at the end of the sequence to show that this one is just going to go on forever. Sometimes a sequence is a function of the term number, meaning you could plug in 1, 2, 3, 4, sort of like on that first slide that we saw, to some rule to figure out the value of the first or the second or the third or the fourth term. So if I wanted to find the 8th term, I could just plug in the number 8 to some function. Or if I wanted to find the 15th term, I could plug in 15 to some function. So here's an example of one that can be written as a function. If the sequence is 3, 9, 27, and so on, the function that defines this sequence, you may recognize that these are all powers of 3, right? This is a power of 3, this is a power of 3, and this is a power of 3. The function is going to be 3 to some power. If we start recognizing the pattern, it's 3 to the power of 1, then 3 to the power of 2, then 3 to the power of 3. So you might be able to figure out that, let's say I wanted to find the 8th term, I would do 3 to the power of 8, right? So that means that the function that's defining this sequence is 3 to the nth power, where n stands for the term number. So down below you'll see a notation note. U sub n is what we use to express the value of the term, where n is the term number that we're trying to find. So basically what this is showing is the function that will get us any term. Now, instead of using function notation like f of n, we're just using a new notation, which is u sub n. And pardon my handwriting here, I'm using the mouse as a writing tool, which is never very good. So instead of using f of n, we're using u sub n, but it means sort of the same thing. It's just a notation that means you can plug in any n value to find any term number that you want. So if I wanted to find, let's say, the 10th term, I would write it as u sub 10, and just like f of 10, we're not doing any math on that side. That's just a notation, and we find the value of the term by plugging in the term number. So if we have a definition like this, it's really easy, a function like this, it's really easy to find any term that you're asked to find in the sequence. You would just take out a calculator, figure out what 3 to the 10th power is, and that would be the 10th term of this sequence. Here's an example from our textbook. So we're going to find the first 5 terms and the 50th term, which we can do because it's really easy to just plug in a number when they give you a formula. So they give us a formula for a sequence. They're calling it b sub n instead of u sub n. U is really common, but you could really use any letter, just like when you're doing a function. You could use f of x, g of x, h of x, right? Any letter to define your function. So here they're calling our sequence b sub n. And they give us an explicit definition. That means a formula that we can plug into. So this is called the explicit definition when you can plug in the term number. You're going to want to get that definition in your notes. That word does come up on exams. An explicit definition of a sequence is one where you can plug in the term number to figure out the value of the term. So here, if I want to figure out the first 5 terms, I'm going to plug in 1, 2, 3, 4, and 5 into this function. And I've done it out here so that the handwriting will be a little bit neater. So I've plugged in 1, and I've gotten 1 as my answer. I've plugged in 2, I get this fraction 7/4. Plug in 3, plug in 4, and so on. So you just plug in and simplify. I did this as if it was on a non-calculator part of the test. So rather than giving decimals, I gave fraction answers. So I've figured out the first 5 terms here. And the other thing I wanted us to find was the 50th term. Well, I can still just plug in 50 into this formula and figure out what the 50th term would be. It ends up being a pretty ugly number, but it's not that difficult to evaluate. Another way to define a sequence is something called a recursive definition. So the one that we just practiced using, where you can plug the term number directly in, that was called an explicit definition. A recursive definition is, instead of plugging in the term number, you have to plug in the previous term to figure out the next term. So this is a definition that is based on the previous term's value rather than on n. So for example, in the sequence 3, 5, 7, 9, you can find each term by adding 2 to the value of the term that came before it. So as you see in this formula down here, u sub n equals u sub n minus 1 quantity, that whole quantity, u sub n minus 1, with 2 added to it. And what does u sub n minus 1 mean? It means the value of the previous term to the one that you're trying to find. Here is another example from your textbook. And the first 5 terms in the 20th term of the sequence, but this time they gave us a recursive definition. And I can tell that this is a recursive definition because instead of being a function just in terms of n, it's a function that has b sub n minus 1 in it, which means the value of the term that comes before the one you're trying to find. So again, I've done this one out and pasted it in so my handwriting will be a little neater. So I'm trying to find the first 5 terms first. Now they have to give us the first term if we're going to do a recursive sequence or a recursive definition. So they tell us that the first term is 5 by stating that b sub 1 equals 5, right? That means the first term is 5. So our first term is 5. To get our second term then, we're going to plug it into the formula, which says 2 times the previous term plus 3. So I wrote it out as 2 times b sub 1 plus 3. And now b sub 1 equaled 5, so then you plug in 5 to the formula. And the value of the second term comes out to 16. Now we're going to use that 16 in the next step. So to get the third term, we have to plug in 16. And that comes out to 38. And we're going to use that 38 to get the next one. So we plug 38 in next time. That comes out to 82, and then we plug in 82, and we get the 5th one. So here are the first 5 terms of my sequence: 5, 16, 38, 82, 170. The other thing I wanted us to get is the 20th term of the sequence. Now, there's nowhere in the formula for us to just plug in a 20, right? In order to get the 20th term of the sequence, we would need to know the 19th term of the sequence. That's what a recursive definition requires. It requires that you know the term that comes before the one you're trying to find. Now, that would take a long time, and I can see that these numbers are getting large quickly. So it's not really that helpful to have a recursive definition if you're trying to find a high term number or any random term number, really, because you have to work your way up to it. So that's what my little note says down here. In order to get the 20th term using a recursive definition, you're going to want to use the calculator to do it. And I'm going to record a separate video that shows how you can plug in a function like this into your calculator and get it to figure out the 20th term or the 50th term or something more complicated. And I doubt that you would be required to do that on an exam, but it's a useful thing to know, and it might show up on an exam. And then the final slide here is that you should know not every sequence can be defined by a formula. Sometimes you can only write them as a list. We have discussed what an explicit definition is and what a recursive definition is. But here's an example of a sequence that you can't really write as a function of n, and you can't write it as a function of b sub n minus 1 or u sub n minus 1, which would be the previous term. But perhaps you can figure out the rule that's being obeyed here if you look at it for long enough. This is kind of a cool sequence. You don't really notice it until you start looking at the later numbers, but you'll see, like, if you look at the 5, the 8, the 13, each value is the sum of the 2 values that came before it. So it doesn't really kick in until the third term, really. If you look at the second term, it's just a 1. And so if you were to add the previous 2 terms, it doesn't really make sense because there aren't 2 previous terms. And so this one is a sequence. It does obey a rule. You add together the previous 2 terms, but you can't write it as an explicit definition. You can't really write it as a recursive definition. But just for those of you that might have thought ahead, I did try to think of a way that I could express this formulaically, and I came up with, so here's the sequence again. The first term is 1, so that has to be defined because each term here is sort of related to previous terms, plural. You could think of the second term as being the sum of the 0th term, which doesn't exist, and the first term. And then you can think of the third term as being the sum of the first and second. And you can think of the fourth term as being the sum of the second and third. And so as I started writing this, I started to realize that there kind of is a pattern here, and you actually can write a formula for it. It's just not really explicit or recursive, because look at what the formula would be. To get the value of any term, to add the value of the term that is 2 below it, plus the value of the term that is 1 below it. So it's sort of a recursive definition, but not quite. So occasionally you will see sequences that can't be written with a formula, but they're not all that common on the IB exam because they sort of want you to be using the ones that you can use a formula to evaluate. Okay, and that is all for this presentation.